Hello everyone, I'm Professor Xiaonan Gao. Welcome to the General Chemistry class. This session will finish the chapter Matter, its Properties and Measurements. This session we are going to cover three parts: the density, the arrows, and significant figures. Here's an old riddle. What weighs more, a ton of bricks or a ton of cotton? If you answer that they weigh the same, you demonstrate a clear understanding of the meaning of the weight and, indirectly, of the quantity of matter to which the weight is proportional, that is, mass. Anyone who answers that the brick weighs more than cotton has confused the concept of weight and density. Matter in a brick is more concentrated than in cotton, that is, the matter in a brick is confined to a smaller volume. Bricks are denser than cotton. Density is a ratio of the mass to volume, written as D equals m over weight. The SI units of mass and volume are kilograms and cubic meters respectively, but chemists generally express mass in grams and volume in cubic centimeter or milliliters. Thus, the most common encountered density unit is grams per cubic centimeter, or the identical unit grams per milliliter, which equals 1,000 kilograms per cubic meter. Mass and volume are both extensive properties. An extensive property is dependent on the quantity of matter observed, like size, weight, and length. However, if we divide the mass of a substance by its volume, we obtain density, an intensive property. An intensive property is independent of the amount of matter observed, like boiling point, color, temperature, luster, and hardness. Thus, the density of pure water at 25 degrees Celsius has a unique value. Whether the sample fills in a small beaker, which with small mass over small volume, or a swimming pool, a large mass over large volume. Intensive properties are especially useful in chemical studies because they can often be used to identify substances. All measurements are subject to errors. To some extent, measuring instruments have built-in or inherent errors called systematic errors. For example, a kitchen scale might constantly yield results that are 25 grams too high, or a thermometer a reading that is 2 degrees Celsius too low. Limitations in an experimental scale or ability to read a scientific instrument also leads to errors and give results that may be either too high or too low. Such errors are called random errors. Precision refers to the degree of reproducibility of a measured quantity, that is, the closeness of agreement when the same quantity is measured several times. The precision of a series of measurements is high if each of a series of measurements deviates by only a small amount from the average. Conversely, if there's a wide deviation among the measurements, the precision is poor. Accuracy refers to how close a measured value is to be accepted, or actual value. High precision measurements are not always accurate. A large systematic error could be present. Still, scientists generally strive for high precision in measurements. To illustrate these ideas, let's see the picture of precision versus accuracy. A tight cluster of several darts near the edge of a dartboard can be considered precise but not very accurate if the intention was to strike the center of the board. If the darts are all close to the center but not very tightly distributed, it's considered to be accurate but not precise. If the darts are not close to the center, neither not very tight distributed, then it is considered to have no accuracy, neither precision. The last one is easy to tell. Since a tight cluster of dots in the center, the distribution has both precision and accuracy. In scientific calculations, sometimes the number is too long to write. For example, the number of the atoms in 12 grams of carbon is this number, very long. So we have to use the scientific notation for 6.022 times 10 to the power of 23. Another example, the mass of a single carbon atom in gram is this. Therefore, we write 1.99 times 10 to the power of negative 23. In the scientific notation, n times 10 to the power of n, the capitalized n is a number between 1 and 10. And the lowercase n is positive or negative integers, the exponents. How do we convert numbers to scientific notations? Let's say two examples. For 568.762, since n is a number between 1 and 10, we need to move the decimal left for two numbers. Therefore, n equals 2 greater than 0. The answer is 5.68762 times 10 to the power of 2. The second example, 0.0000772. This time, we need to move the decimal right for 6 numbers. n in this time is less than 0. And the answer is 7.72 times 10 to the power of negative 6. This scientific notation calculation is pretty easy. For the addition or subtraction, first step is to write quantity with the same exponent n, and then combine n1 and n2. The exponent n remains the same. Let's say an example. 4.31 times 10 to the power of 4 minus 3.9 times 10 to the power of 3 equals 4.31 times 10 to the power of 4 still plus 0.39 times 10 to the power of 4. And therefore, the answer is 4.70 times 10 to the power of 4. For multiplication, first step is to multiply n1 and n2, and then add exponents n1 and n2 together. For example, 4.0 times 10 to the power of negative 5 times 7.0 times 10 to the power of 3 equals 4.0 times 7.0 times 10 to the power of negative 5 plus 3. The answer is 28 times 10 to the power of negative 2, and therefore 2.8 times 10 to the power of negative 1, because this number is in between 1 and 10. For division, first step is to combine n1 and n2, and then subtract exponent n1 and n2. For example, 8.5 times 10 to the power of 4 over 5.0 times 10 to the power of 9 equals 8.5 over 5.0 times 10 to the power of 4 minus 9. And the result is 1.7 times 10 to the power of negative 5. Significant figures are digits that carry meanings in a number and contributes to its precision. Any digit that is not 0 is significant. Like 1.234 kilogram, there are 4 significant figures. 0 between non-zero digits are significant. Like 606 meters, there are 3 significant figures. Zeros to the left of the first non-zero digits are not significant. like 0.08 liter, there's only one significant figure. If a number is greater than 1, then all zeros to the right of the decimal point are significant. Like 2.0 milligram, there are two significant figures. If a number is less than 1, then only the zeros that are at the end and in the middle of the number are significant. Like 0.00420 gram, there are three significant figures. Let's work on an example to understand the calculation of significant figures. How many significant figures are in each of the following measurements? 24 milliliter, two significant figures. 3001 gram, four significant figures. 0.0320 cubic meter, three significant figures. 6.4 times 10 to the power 4 molecules, two significant figures. 560 kilogram, three significant figures. How do we perform calculations of significant figures? For the addition and subtraction, the answer cannot have more digits to the right of the decimal point than any of the original numbers, like 89.332 plus 1.1. There is only one significant figure after the decimal point for 1.1. The answer 90.432 should be rounded off to 90.4. Similarly, for 3.7 minus 2.9133, there are two significant figures after decimal point. So the answer 0.67967 should be rounded off to 0.79. For the multiplication or division, the number of significant figures in the result is set by the original number that has the smallest number of significant figures. 4.51 times 3.6666. There are three significant figures for 4.51, so the answer has to be three significant figures, 16.5. For 6.8 over 112.04, since 6.8 has two significant figures, the answer should be rounded off to two significant figures. Then it is 0.061. There's only one more point you have to pay attention: the exact numbers. Numbers from the definitions or numbers of objects are considered to have an infinite number of significant figures. For example, what is the average of three measured lengths: 6.64, 6.68, and 6.70? The average of the three numbers is 6.67333. Since there are all three numbers have three significant figures, the answer has also possess three significant figures, which is 6.67. Because 3 is an exact number here, so the answer should not be rounded off to 7. Alright everyone, in this class we learned the density, arrows, and significant figures. I hope you have enjoyed the class, and I'll see you next time.